Welcome to classes on physics. Today's topic is today's topic is nuclei, and it is class number 6 higher secondary second year. You kindly follow the class. I will make the class a bit fast and I will explain all the key points, and later on I will go on solving the questions problems, and so also at the last of this class I will solve all competitive exam questions. Mindedly follow from beginning to last of the conceptual classes first, then you can very easily understand to solve out the different critical problems which appears in the competitive exam. Since the topic is nuclei, natural educations of nuclei, that is nucleus of atoms or nuclei of atoms. So before that you have got some idea regarding this from the Rutherford model. There is a nucleus. I have got this idea, and from the Rutherford I have got about the knowledge of nuclei, that is about its volume, about its size. Now we will come regarding this density and more other terms relating to nuclei or nuclear physics. It is a very important chapter from physics point of view, chemistry point of view also. Inside the nucleus, there is proton and neutron, and as a whole it is called nuclear. Neutron, which was first discovered by James Chadwick. James Chadwick in 1932. Basically, we know that the main constituent of nuclei is proton and neutron. However, later on during my discussion, you will find that there are a lot of other particles which are also appears during the exchange mechanism, and these things are mesons, bosons, freons, positron, J-side meson, epsilon meson, during our discussions we will come that other particles which are some of our massless particles may also present during the transformation or exchange of neutron and proton. In exchange theory we will get it. These mesons, bosons, freons, positrons, J-psi mesons, epsilon mesons, and glucon, which is massless. A lot of particle, intermediate particle may also present in the nucleus. So before coming to this one, first of all, we should have some knowledge. I will not define. A is mass number, Z is atomic number, number of neutron is m minus z, because these things again will come in need in finding out the mass defect. So already you have got this in chemistry. Again, I am just recalling the facts once again for your clear understanding, so that you can find it easy to understand in later part of the topics. Next, regarding this other related isotopes, topics are isobars, isotones, isomers. Again, I will find it necessary to discuss all these facts because it is known to you. Isotopes, the different species having same atomic number with different mass number. Isobars, different species with same mass number, different atomic number. Isotones, different species with same number of the neutron, as you calculate like this. And isomers, these are same topics, these are same elements having same atomic mass and mass number, but different state of energy. Say one is in excited state, one species in excited state, from this it has transformed into ground state. Say the species X, ZA, X, ZA. This is excited state and this is ground state. Excited state of species with atomic number Z and mass number A has changes or transformed or come to its ground state by X, Z, A, means atomic number and mass number are different but energy state are different. With emission of some particle is gamma will come later on. These type of species are called isomers. Again, from background I am telling the size of nucleus from Rutherford model. It is of about 10 to the power minus 14 meter. Size of nucleus, diameter of atom is of this much. Now again from the book, the density, it is very important factor. This time in CBSE higher secondary 2 question appears. I will explain in course of my discussion. Density of nucleus. First of all, I will tell density of nucleus is independent of size of nucleus. That question was asked. You have to show or explain in 1 marks that density of nucleus is independent of size or mass. So what is density? Let us first write we know the volume of the spherical particle is equal to 4 by 3 pi r cube. R is the radius, is proportional to the mass number. From this relation we can write that r cube is proportional to mass number, r is proportional to a to the power 1/3, or r is equal to r naught into a to the power 1/3. R naught is a constant whose value is equal to 2.1 into 10 to the power minus 15 meter. Am I right? We have got a relation of radius r is equal to r naught a to the power 1/3. What is density? Density is equal to mass per unit volume. What is mass of the nucleus? Say it is mass number, and average mass of the nucleon means proton and neutron is small m. So m into a, and the volume is equal to 4 by 3 pi r cube. On solution you will get. So from the derivation of density we see that density is nothing but thrice m by 4 pi r cube, no a term, that is mass number, that is volume, that is size is not involved. That is size, density of a nucleus is independent of the size or volume or mass number. From the relation we can say. Simple explanation, nothing difficult, you can understand very easily. Now bit by bit we are approaching towards the main part, nuclear force. Before discussing nuclear force, let me point out three types of force. One is gravitational force, other is electrostatic force, other is nuclear force. Three types of force: gravitational, electrostatic, nuclear. Before that, I am telling you that is of order this, that is nuclear force is the highest, electrostatic force is 10 to the power 36 and gravitational force is 1. The ratio is like this. So for your clear understanding, that just keep it in your mind. I will apply this fact a bit later on. So let me come to the point, nuclear force. What is nuclear force? Means inside the nucleus, what's happened? There is neutron and proton that are nucleons, and the distance between nucleon is this much. That is very meager, very small, very small. So naturally there is a question, if you talk about the nucleus of an atom, say nitrogen, say oxygen, in nitrogen there are 7 proton, or oxygen there are 8 proton, am I right? 8 neutron, like this. So if the number of proton in the nucleus is more, so naturally there is one type of interaction is proton-proton repulsive interaction is there. So one is proton-proton interaction, repulsive interaction, and other is, so neutron and proton, every materials in the universe has some kind of attraction, that is gravitational force of attraction. So there is some attraction force. It is seen that repulsive force of proton-proton charged particle is much more higher than gravitational force of attraction. Means nucleus should not be stable. But in actual practice, we see that nucleus of an atom exists. So it means that there must be some amount of force which binds nucleons all together in the nucleus so that atom exists. So the attractive force which binds the nucleon in the nucleus of an atom is called nuclear force. Am I right? The attractive force which binds nucleons in the nucleus of an atom is called nuclear force. So there must be some force which overcomes each kind of repulsive or attractive, any kind of attractive or repulsive force which overcomes the nuclear force. That nuclear force has bind this one, that is called nuclear force. But again, we don't know what this is. What it is, we don't know. Bit by bit, we are coming. What's happened? ECOA, YUKUWA, a Japan scientist of Japan in 1935 put forward exchange energy, a theory, exchange energy. He tells that neutron and proton exist due to the exchange of some particles called meson. MESON, meson. Means due to exchange of meson, the proton and neutron exist. Means proton as a whole does not exist as proton, and neutron as a whole does not exist as neutron. They at one time frequently changing into meson, proton, meson, neutron, proton with some charge, that was massless particles through which they come there. That's why during this exchange lots of energy evolves outside. That energy is responsible for binding the nucleon in the nucleus, and that energy is called nuclear force. Am I right? So one of the term I explained the exchange energy from Ikawa theory in 1935, which is a Japan scientist who put forward this theory. Now, in short, I am telling a lots of things here we have to mention. Now, next, there is a question that if what is the modern concept? Modern concept, that is subatomic particle inside the nucleus has subunit, has some subunits, and these subatomic particles has subunit. That subunits are called quarks, and quark force arises due to the exchange of massless particle. Quark energy arises due to exchange of massless particle called glucon, and that gives rise to the force which is called nuclear force, which are responsible for binding of nucleons inside the nucleus. In short, there are some theories I have explained, but one of the small point I have missed out about density, which I told that density is independent of mass or size. Am I right? So what is the density of the nucleus in terms, what is the order? Density of nucleus order is 10 to the power 17 kg per meter cube. You imagine this is a very huge density of the nucleus, because if you compare the density of water, the density of water is 3 kg per meter cube. So with the comparison of density of water, we can see that density of the nucleus is tremendously high. Such density, type of density exists in neutron star. So in short, I am telling you what is neutron star. When the bright or giant bright stars after supernova explosion, the core part of the star comes out, which is termed in short as neutron star. Means there is a specific time of the star's sun, 6 million years, the specific life period of sun. Like star has specific life period. After this stars destroying. During the time of destroying, in the sphere around the star, we may get phosphorus, sulfur, silicon. At the very end, when the time ends, that stars start decaying or collapsing. At this time, the iron starts polymerize. So due to this, the stars come to at that point with the outer sphere excluded out and inner sphere, and the dense iron polymers comes out as neutron stars. Sometimes that neutron stars also give some light. It is another fact. Some sparks. Now, do you assume that this neutron stars, which is the nuclear part, is so dense? Do you know the electromagnetic field? You cannot assume that the magnetic field of Earth is 0.5 Gauss, and that of neutron star is of the order 10 to the power 12 Gauss. You cannot imagine huge magnetic field is there. And when 2 or 3 such type of neutron stars get together or combines up, that gives rise to black hole. and that black hole has an immense magnetic field. It can attract each and everything, even light. That's why it is black. It is another part. I am not going to the story of all this. For your understanding, I have just mentioned the so dense the nucleus, neutron star's nucleus is. Now come to main point. The stability, nuclear force. We explain what is the stability of the nucleus. The stability of nucleus, stability depends on various factors, but one of the very important factor I here want to mention is neutron by proton ratio. Neutron by proton ratio may be 1, may be greater than 1, may be less than 1. For some medium particles, say nitrogen, if you tell about nitrogen, it is 7, it is 4, it is mass number, it is atomic number. So neutron is 7, proton is 7, the ratio is n by p is equal to 1, it is stable. So as you move towards the end of this, out of this Bismuth 83, 84, 81 onwards, you will find that the ratio of neutron by proton, you take example yourself and find them more than 1. Some other lower atomic number molecule, if you just find out the neutron proton ratio, you will find like it is less than 1. So the fact is more than 1, less than 1 are unstable. Equal to 1 is stable. So why the instability occurs is due to the fact that, let me explain some of the important topic relating the stability of nucleus. One is mass defect. Important term, mass defect. Mass defect. I want to like to spend much time on it. It is this defect of mass, say del m equal to mass of proton plus mass of neutron minus m. What I want to mean that if you take the rest mass of oxygen, you will find say 5 AMU, just arbitrary I have assumed, not accurate. But if you now calculate the nucleus mass is the mass of the atom, so in oxygen, in the nucleus, there are 8 proton and 8 neutron. What is the mass of proton? Proton is equal to 1.672 into 2 into 10 to the power minus 27 kg, and neutron is almost the same, 1.67 in place of 2 it is 4, like this, almost same. Now 8 into proton and 8 into neutron, and you add up, you will find, say it will be a bit more than this, it will be 6 mu. So you are getting change in mass. The change in mass is called del m. So constituent part of the nucleus means nucleon. You find out, you will get 1 mass, and you take out all the atom as a whole, you will get 1 rest mass, and you subtract these two, you will get some difference in the mass, and that difference is called mass defect. Why there is difference of mass? Because due to this difference, the mass which has been lost or which is less has been used as energy according to Einstein mass energy relation, and that energy is utilized in binding up of the nucleon in the nucleus. That hence there is some loss in mass occurs in such calculation, which is called mass defects. Now means that energy, that mass is converted into energy, and energy is utilized in binding the nucleon inside the nucleus of an atom. That is, it is called binding energy. Binding energy is equal to del m c square, where del m is the mass defect and c is the velocity of light, 10 to the 8 meter per meter whole square. Am I right? So again we have got another term, binding energy. Now another point is packing fraction. Packing fraction means if you take the mass defect below and if you divide it by mass number, you will get packing fraction, and that packing fraction may be positive, may be negative. If it is positive, it is unstable. If it is negative, it is stable, because that amount of energy which is negative is found to be utilized in binding the nucleon inside the nucleus. So we have got the term del M, bonding energy, and packing fraction. Now, since we have seen there are some chances of instability of the nucleus, means it indicates that nucleus may break. So a new things or new phenomenon arise, that is called nuclear reactivity. Nuclear reactivity. What is nuclear reactivity? Better, radioactivity means when the nucleus undergo, it is spontaneous What is the radioactivity? Means it is nothing but a process of spontaneous disintegration of atomic nuclei to emit some particles like alpha, beta, gamma. When the nucleus spontaneously disintegrated, broken into pieces, means it will give rise to a newer atom with emission of some particle, and this process is called radioactivity. And that was first uh, given by Becquerel. Hence, there is a unit of radioactivity is Becquerel, that is one disintegration. Other co-pioneer of the radioactivity is Madame Curie and Marie Curie, and also Curie is 3.7 into 10 to the power minus 17 Becquerel. So let me tell something about alpha, beta, gamma ray. In terms of representation, we'll represent it as helium, and it is represented as S -1 E0 mass 0, and it is not represented in any way at all. In terms of charge, it is positive charge, it is negative charge, it is chargeless. In terms of mass, it is and it is the same as electron. It is rest mass is 0. In terms of deflection of magnetic and electric field, it is attracted towards negative pole, electric and magnetic field, and since it is negative, towards positive pole, not deflected at all. In terms of ionizing power, it has mean ionizing power, so we'll take it as a comparing factor. This is 10 to the power 2 times of gamma, and it is 10 to the power 4 times of gamma. In terms of penetration power, it is ionizing power. It is highly energized particle, highly energized particle. and here its penetrating power is minimum. So we'll compare others in terms of alpha. This is 2 times of alpha and this is 4 times of alpha. This is in short the properties of alpha, beta and gamma. This is helium, this is -1 E naught, this is highly energetic particle, it is positive, negative, nil, mass number is this, mass is 9.1 or mass rest mass 0, ionizing power is 10 to the 4 times of gamma square times of alpha gamma, and it is minimum. Penetrating power is minimum and it is 10 square times of alpha, and it is the highly penetrating power, most energetic particles. So this is in a nutshell something about alpha, beta and gamma and their properties. This is one of the very important statement here is that I'll not define anything. I will explain with practical example. You can very easily understand. You need to give the definition. You can yourself write the definition. That is, when a nucleus is subjected to emission of alpha particle, what happens to it? Say, this is atomic number A and mass number is, atomic number is Z, mass number A. If there is loss of alpha particle, means helium 24, atomic number 2, mass number 4 loss. That particle, that atom will change with newer atom with atomic number Z minus 2 and mass number A minus 4. That when alpha particle is lost from an atom, so what's happened? Its atomic number is reduced by 2 and mass number is reduced by 4. Means it indicates that if it is, say, group number is here given, if it is in 14 group, if this is in 14 group, so on losing an alpha particle, it has lost 2 atomic number, means it will reverse back to 14, 12, 11. So 11 group is not there, actually from 13, 14, 15, 16 group. Am I right? So if it is, say, in 15 group, and if it loses 1 alpha particle, it will back 2 unit left, that is, it will be a member of 13 group element, and mass number will be decreased by 4 unit. This is very simple, alpha particle loss. Now what's happened if the same thing, if beta particle is lost, beta means -1, 0. On losing -1, X again will become a newer thing because there is a change in the atomic number, so element will change. It will not be X, it will be, say, Y. Now when there is loss, there is minus, so minus of 1 unit, this minus become plus, minus and minus become plus, so that will become Z plus 1 and atomic number will not change because here above mass number is 0. A minus 0 is equal to 0. Means if it is in 15 group element, on losing a beta particle, it will move 1 unit towards right, it will be a 16 group element. without any change of mass number. Now, what will happen if there is loss of gamma particle? Earlier, very beginning, I told you, if there is loss of gamma particle, it is in excited state, it will become in ground state. This will simply give a gamma ray emission without any change in atomic number and mass number. This is very simple regarding rule, but Sodi has told something about alpha and beta. I have just given you extra something. Now, what is decay? Decay means when there is a disintegration of an element, there is an element, when it transforms into other element, is emits out some particle, and the emitting of some particle is called decay. So, what is radioactive decay rule? How will you define mathematically? Say n is equal to number of nuclei initially, that is at time is equal to 0, at time is equal to t after some time, and n naught is equal to number of nuclei after time t. N naught is the number of nuclei initially, that is at time t is equal to 0. Now, what is the rate? dn by dt is the rate of decay, that is change of radioactive nuclei with respect to small time, dn by dt. It is found that minus dn by dt is proportional to number of nuclei after time t. After time t, the rate of decay is negative, means it is progressive, is proportional to n, then minus dn by dt is equal to some constant into n. That constant alpha is called decay constant. Am I right? Now, minus dn by n is equal to, or dn by n is equal to minus d dt. On rearrangement, we have got this, nothing to explain. On integration, means integration dn by dn by n, it is a constant dt. So, what we get is ln n is equal to number lambda and dx x is equal to x plus some integral constant c. Now, we want to calculate the value of c. From this equation 1, we will assume that at time t is equal to 0, at the very beginning I told you n is equal to n naught. The nuclei, radioactive nuclei is n naught, initial radioactive nuclei, number of radioactive nuclei. So, here from 1 we get ln n become n naught minus lambda t plus lambda at time 0, that c will remain c, that we get ln n naught is equal to c. When we put this value in 1, what we get is ln n is equal to minus lambda t plus ln n naught. Simply, with side change, we get ln n minus ln n naught minus lambda t, or ln a minus ln b is equal to ln a by b, simple logarithmic rule, or since there is base e, we can write n by n naught is equal to e to the power minus lambda t, or all formula will come in neat, or n is equal to n naught e to the power minus lambda t. These are formula. Again, from this we can write what? If you change in logarithmic form 2.303 log n by n naught is equal to minus lambda t, or 2.303 log n above n below n naught n, the sign will change. Am I right? So what we get here is, this is another relation. Now from this rate law, radioactive decay rate, we will define T half, which very often asked in your question. What is T half? Half-life period. It is the time in which the original sample of radioactive nuclei will get reduced exactly to the half of initial. The time in which the initial concentration of nuclei reduced to half is called half-life time. Simply I have defined it. So if we can also write 2.303 by t is equal to n naught n is equal to lambda. So from here we will define T half. Let's see, very simple. If T is equal to T half, so at T half what will happen? That n concentration will become half of the initial, because from the definition it is the time in which the concentration become of nuclei become exactly equivalent half of the initial. So at t is equal to t half, n is equal to n naught by 2. So from this we get 2.303 divided by t log n naught by 2, that is equal to lambda. So if we will take it out, you will go log 2 will above and n naught will cancelled out, we will get 2.303 t log 2 is equal to lambda. Am I right? So very simple mathematical calculation, nothing to explain, very simple, as easy as class 4-5 mathematics. So 2.303 and the value of log 2 is known to you all. Am I right? And that is equal to, sorry, t is equal to t half. So t half, that is equal to lambda. Again, you know, when we multiply, this term is very simple. In chemical kinetics I have explained in second year class the shortcut. This shortcut of this is 693. Always 2.303 into 0.310, 3010 is equal to 6.93 equal to t half is equal to lambda, or t half is equal to 0.693 by lambda. So in your question it is asked, find the expression of T half, and you tell that, you show that it is independent of initial concentration of radioactive nuclei. So no initial concentration term appears in the expression of T half. Hence T half of a radioactive substance is independent of initial concentration of the substance. Now another point here is mean life. Mean life, it is the, I am not defining, average time in which the radioactive nuclei exist, means radioactive substance each and every one has an half-life. So after this time occurs, when its time occurs, that will reduce to half, again half will be again half of half. In this way it will go and diminish and diminish. So at the time when this nuclei exist, average time, that average time of existence of nuclei is called mean time, and it is designated by tau. And you are asked to deduce a relation between mean life and t half. Mean life and t half, what is the relation? Again, very simple relation. In a very simple way we can find out. We know lambda is equal to 0.693 divided by t half, or t half equal to 693 by lambda, all the same, and tau is equal to 1 by lambda, it is known to us. So if it is lambda, therefore 1 by lambda is equal to t half divided by 0.693. So we will write tau is equal to 1 by lambda is equal to t1 by half, 0.693. That is, tau is equal to t half, or you can write 1 by 0.693 into t half, and if you calculate you will get it is 144 into t half. That is, mean life is equal to 1.44 times of the t half is the relation between mean life and t half. Am I right? Very simple, nothing tough. Again, very important mathematical formula, you please keep it in your mind. Amount of radioactive substance remain undecayed is equal to very important, very often asked in class exams, also in the entrance exam, very often asked. The when you see the radioactive substance undergo disintegration, it will start decaying of within half of the half period after half period. Sometimes you may be given that after some period how much amount of this radioactive nuclei has remained undecayed. So the formula is initial concentration into half to the power n, where n is the number of half-life period, and this number of half-life period is the total time divided by time of the half-life period. Total time divided by time of half-life period is equal to n. I will give you the explanation or example, and I will show you how to solve out the problem. You take an example. Already I have told you when alpha particle is lost, what happen. I have already showed is an Fajan rule, group displacement law. I have told you. Say uranium, it is 92 and 232, and when alpha is decayed, means here 2 will be less from the atomic number, means it will be thorium, and here 4 unit left, means twice 34, and you will get here alpha particle and some amount of energy will be released. Such type of reaction is called alpha decay. Now if you say it is beta decay, say you take an example, sodium atomic number 2, mass number say 23. What does beta decay mean? Means here sodium beta means -1 0, -1 become plus, so minus 1 will be plus 1, and this will be magnesium, and mass will remain same, and this is beta E naught. Now what is gamma decay? I told you that a bit earlier that if it is J, if it is A, if it is in excited state, so that Z and A will remain same, and amount of particle released is termed as gamma, that is called gamma decay. I have taken a very simple example, so with the help of which you may be asked, and very often asked in entrance, you are asked to find out the number of alpha and beta particle emitted out from this change. What's happened? Thorium 9232 has changed to lead 82208, and you are asked to find out number of alpha particle and number of beta particle which is emitted in transformations of thorium to lead. And lots of examples or lots of way are also mentioned in the books, and here I will show you very short and easy way so that you can very easily find out number of alpha particle and beta particle to be emitted out. So to solve out, we'll do what? We'll write thorium 9232 has changed to lead 201, and let us assume an alpha particle this. How much alpha particle is been emitted out is n alpha particle. Now the matter is that if you equate out the above, it will give you alpha particle, and if you equate out the below part, it will give you beta particle. So on equating the above part, (4n), am I right? What we get here is that is 4n is equal to 24, am I right? N is equal to 6, and this is number of alpha particle. Now if we equate the below part, 90 is equal to 82 plus 2 into n, so you are getting 8 is equal to twice n, n is equal to 4. This will give you the number of beta particle. Very simple, nothing to explain. Equate up upper part, you will get alpha particle. Equate below part, you will get beta particle. Other problems, other methods are there also, you can try it. I think this is very simple and easy way to solve alpha and beta particle, very often asked in entrance. So in mid of my discussion, I am showing you so that you will find it easy in this, solving out the we know n is equal to n naught half to the power n. This is the formula. You are asked that T half of a radioactive nuclei is radioactive nucleus is 1600 years. T half of radioactive nucleus is 1600 years. After how many years 25% of it will remain undecayed? So n is equal to n naught equal to half. 25% means this much. 1/4 of the initial is 25. 1/4, what is the percentage? 1/4, the percent 1/4, if you take a percent, you will get 25%. 25% means 1/4. So 25% will remain undecayed, means that one will be 1/4 made 25%. So this is half to the power n. So we'll cancel out, we'll find half. 1 by 14 is equal to half, half square is equal to half to the power n. So we get n is equal to 2. So decay constant time is equal to t half into n. What is t half? 1600. What is n? N is equal to 2. Integration is equal to t half into n. So t half is equal to 1600 years, and n we have calculated here is 2 half years. N is the number of half years, equal to 2 half years is equal to 32 years. 100 years after we will get 1 by 4 remain undecayed. Yes, the last part, I think the question, the chapter has a bit lengthy, has become a bit lengthy. So within a minutes, I'm going to close the chapter. Here you see some type of induced type of reaction. Here it is called alpha proton, alpha induced reaction. Deuterium neutron, deuterium induced reaction. Proton gamma, proton induced reaction. Neutron alpha, neutron induced reaction. Means the alpha is the initiator of the reaction, so alpha induced reaction. Here deuterium is the has induced the reaction. Here proton has induced the reaction. Here neutron has induced the reaction. Am I right? So let us write the answer. What's happened? It is alpha induced reaction. It is this. Alpha means twice helium 4, and you are asked it is carbon. Am I right? So you give carbon here, and when alpha is there, alpha here there is proton. You write proton first. So also now you see in below 5 plus 2 7. Already you have got 1. To balance it you need it 6. So it is 10 plus 4 14. You have got already 1. That should be 13. You don't give here 14. So you balanced. You first you write alpha, and here it is given proton. You write proton first. So you are getting below 5 and 1 7. You have got already 1. So make it 7. We need 6. So it must be 6. And it is 10 plus 4 14. So 1 is already there. It must be 13. Don't give it is 14. Am I right? Or 12. You need to do as you like. So come to this one. Carbon. If it is question is given in this way, you are asked to write the answer. It will be this carbon 6 12. Deuterium induced reaction. What is deuterium? It is 1H2. And what the answer we get here is nitrogen. Am I right? Nitrogen. I don't know what is the its atomic number must be 7. No doubt must be 7. And what we get here is Newton. What is Newton? Newton is this. The symbol is this. So 617707, and here 12 and 2 14. We have got 1 here. We need 13. This is how we'll solve. Now come to this one in a very speedy way. This is this proton gamma. What is proton? Proton is this. What do we get? Oxygen. Atomic number of oxygen must be 6. It should not change. So what we get here? Gamma. So no change in gamma. So you are getting 7 and 1 8. We have got 1, and 14 1 14 and 1 15 will give it here 15. Last one is sodium. It is 11. It must be 11. It may not be given. You should give it 11, and it is Newton. Newton induced reaction. So Newton is here there. So what we get here is not given. So you did one things 11 and 0. This is 11. 4. Here we have got 4, and that should be. I'm sorry. Here that there is some mismatch of the total. So we should write helium first. So we have written helium. So we have got 2 here, and we need 11, total 11. So to make it 11, we need 9. 9 means fluorine. It should be fluorine. So This is the end of today's class with last part with nuclear type of the nuclear reactions with emphasis on the fusion reactions and fission reactions. I'll conclude the class, and with the next class with the new solutions of the competitive exams I will appear. Thanks a lot for watching the class.